Oh, okay. All right, welcome back, everybody. We are now recording the second session. This is going to be concentrating on how to obtain a spectra of the supernova SN2022 HRS. So we have on our screen right now a V-band image. So let me start going back to the live view, which I'm going to click on continuous. I'll start doing 10-second exposures. And the thing about the spectroscopy filter is when you put that in place, everything is a lot dimmer because you're spreading out the light across a larger area, and it shifts the image also vertically, so that in order to get the spectra to fit on our screen, I know from experience I have to reposition our target down toward the bottom of the view. So the way I'm going to do that is I'm going to use this little hand control window. And this is how you would do it if you were using the telescope, is you can actually move the telescope in real time by using these NESW buttons here. So what we're going to try to do is get the supernova down towards the bottom of the view. And I'm going to just slide the view up a little bit here so that we can see more toward the bottom. Now, I know from experience in the past that south is up in this view. So obviously I want to move the scope to the south to move the stars down. So I'm just going to push, I'm going to depress the S button just a little bit on the hand control, just to confirm that we see everything drop down a little bit in our view. And it should here in just a moment when the next screen refreshes here. Okay, did I go the wrong way? Maybe I did go the wrong way. Let me go back up here. Let's wait for it to come in again. Yeah, silly. I went the wrong way for some reason. Okay, let me go. I'm going to press the north button. North button is going to move it down because we want the target star near the bottom of our field of view because the spectrum will be above it, and we want the target star and the spectrum to fit in the view. Okay, that's moving correctly now. All right. I'm going to slow our slew speed down just a little bit to 8 times sidereal. All right. And go a little bit again. We're going to move it down a little bit more again here. And I got to go a little bit further. All right. That's going to be getting close in just a moment. We get our next image up. We'll see it move down a little bit further. Okay. I think that's going to be good. Let's wait for the next one to come in. All right, so here's the very bottom of the frame. By using that slider bar, I was able to look down at the very bottom. So that looks good. So now what we're going to do is we're going to move the spectroscopy filter into view. So to do that, we stop the exposure. We go over to the filter wheel window, click on the tab, and then we can see all of our different filters here. Open Star Analyzer. We were doing the V-band before. We're going to have to do the Star Analyzer now. So we click on Star Analyzer. And I'm going to start taking a series of 10-second exposures. Now, the problem is that, again, every time you put a different type of filter in, you have to retweak the focus. So when you're not using any filter, the focal position is what it is. When you put the V-band filter in, the focal position changes and you have to refocus. When you put the Star Analyzer in, the focus position is different again. So we're going to have to tweak the focus just a little bit here, like we did when we were doing the V-band image at first. Okay, so is the let's see, we got the Star Analyzer filter in. Let me just, so we should see the spectrum. I don't see any spectras here. All right, let me just try this. I don't know if the filter moved in place. It says Star Analyzer. Let me just hit stop. All right, Star Analyzer. Let's try it now. It says filter moving. So from what I can see here, we should be, and everything down here in the window says we are using the star analyzer filter. So, okay, let's try again here. Maybe I didn't click something that I thought I did. Still, don't think that's it. Now, we must have a filter wheel issue here because we didn't change filters. So what I'm going to do here, I'm going to try to fix it by disconnecting and reconnecting. Let's just see if that helps. I'm going to disconnect the camera. Cool it off. Sometimes you have to disconnect the camera, and sometimes that works. At other times, the fix would be I have to go out and actually physically unplug the USB cable and replug it back in, and then it wakes back up. But I think we have a sleeping filter wheel. Okay, turn the cooler back on. Oh, wait a minute. Wait. What's this? We have two camera control windows open. That's because I had two instances of the program running. That was probably the other camera window. Oh boy. Okay. That's why. Okay, now we go down. Let's go here. This is the one that's we should be using. So never open more than one circumstance of a program. Otherwise, you're just going to be asking for trouble. Let's see what happens here. Let's see if this does it. That was the other one that we were using though earlier. All right, let's just see what happens here. Now, something was taking too long there. I'm kind of puzzled as to what's going on here, but let's just see what we get. It's taking too long to read. I will stop that. Okay, so we have a connectivity issue here with Maxim DL. What I'm going to do is I'm going to close out everything. I'm going to close out all the Maxim DL windows here. And let's close out everything. Pull it off. Disconnect. Okay. Now I'm going to scroll down to the bottom, make sure we have no instances open of Maxim DL. Got this one here. That's it. Okay, good. Okay, so now let me start over. Let's just open up Maxim DL again. The good thing is we're still on our target. The scope is still tracking. Everything is good there. All right, so let's reconnect the telescope and the focuser. Okay, that looks good. Let's go to our camera. Let's connect our camera. It's cooler on. We should see the temperature dropping, and it is. Okay, that's good. So everything looks good on the screen here. Let's go to our exposed tab. We're going to be on the star analyzer filter. That's good. 10-second exposures, continuous. All right, let's see what we get here. Hopefully we see vertical lines on the screen here. Yes, there it is. Okay, we're good. Now, what we see here is that object is the galaxy, and that smear at the top is its spectrum. So we want the supernova, however. And so that's a little bit too faint to show up on this, because remember I was saying this filter really spreads out the light. So what I'm going to do here basically is just use this to just check the focus. I want to make sure that the focus looks good. And it does. When you're doing spectroscopy, you don't really focus on the stars. You focus on the lines, and you want them to be as thin as possible. And what I like to do is I like to change the scaling a little bit to display a little bit less graininess. It helps me focus better. And so I use the planet setting on the screen stretch. So it looks pretty good. Our supernova is right here. There's our supernova. So its spectrum is going to be a little bit lower than the spectrum of the galaxy. So as long as that galaxy spectrum is all the way on, and it is, we should be good. Okay. And that focus looks pretty close. That's a nice narrow line there. So let's give it a try. Let's take a single 60-second exposure. So let's just do a test exposure here. And let's make sure we're in good focus. We have to go long exposures on the spectroscopy, because this filter takes the light from that point and spreads it out over a large area, which means you need either a long exposure to make up for that spreading, or you need a big telescope. So we don't have a big telescope. Our telescope size is what it is. It's 10 inches. So we have to go a lot longer on our exposure to get these spectra to show up. So fortunately, the tracking on this telescope is very accurate. It uses the TDM telescope drive master to keep it tracking very smoothly, very accurately. So we can go long exposures without needing to auto guide. And what we should see when this comes over is we should be able to see both galaxies and the supernova and its spectra. And if it looks good, we'll set up our autosave sequence and we'll get some spectroscopy data. So there's M60. There's the galaxy. There's our supernova right down there. So there it is. Okay. So this is our supernova right here. This is NGC 4647 right here. Doesn't look like much, I know. But when we stack our images, we will get a nice spectrum. And hopefully we can see a spectra. There it is. This is our spectrum right here of the supernova, right there. See how dim that looks? Believe it or not, that's usable. So what we're going to do is we're going to take a series of exposures and we're going to stack them together, and we'll get a much more clear image of that spectrum. And then we'll use that stacked image in our analysis programs to analyze the spectrum. And that's what I did last time. So, all right, so let's do that. Let's go ahead and set up a series of 60-second exposures. We hit continue. I'm sorry, we go to autosave. And we're going to be using our spectroscopy filter. So we turn off the number 2. We don't want the V-band filter now. We want to go down to star analyzer at the bottom, number 6. Exposure time is going to be 60 seconds. Readout is normal, binning 1 by 1. Everything looks good. Now we got to save it. We got to set the image save path. Remember, we created a subdirectory when we were doing our V-band of photometry. Well, now we want to create a subdirectory under tonight's date for spectroscopy. So now our data will go into this folder. And there, click OK. All right, and OK here. And we hit start. And here we go. So now we are going to be getting, we are now taking a spectra. Here it is right here. That faint line, you can kind of see how it's broken up. It's not continuous. Compare it to some of the other ones you see on the screen. You can see there's a break in it, right? Right in this area right here. Looks like there's a break there where it stops. There's another one maybe right here. Those are actual spectral features in the spectrum of that supernova. And it will be much clearer when we stack our images. So this might be as good a time as any to talk about how we obtain the really nice, clear images that we do when we're photographing very faint objects like this. So we could go longer on our exposure. I could go 120 seconds or even 180 seconds if I wanted to. However, the calibration frames that I have, those are the ones that are used to make this data that we're seeing more scientifically useful, are calibrated for 60 seconds. So until I create new ones, I'm going to stick with 60-second exposures. And that's okay. Our 60-second exposures will be enough when we take 10 of these and we stack them up one on top of the other using a stacking software, which MaximDL will do. It will make that spectrum pop out. It'll be a lot easier to see, a lot brighter, and it'll be workable. So you can kind of see down here at the lower right, here's the spectrum of a star on the right-hand side. That's nice and uniform, not much really to see there. And spectrums basically are fall into three types in general. They're either continuous, which means that the spectrum is fairly smooth without any noticeable features, or if the features are there, they're very subtle. Or it could be an absorption spectrum where there's areas that are darker in the continuum. So you'll see dark features, those are absorption features. Or it can be an emission spectrum where there are parts of the spectrum that are noticeably brighter than the background. And so you can have any number of those combinations in any spectrum. So you can sometimes have one spectra show, all three different features, depending on what kind of object you're looking at and depending on what type of physical processes are occurring in the star's atmosphere to create those various types of features. And it's way beyond the purpose of tonight's lecture or course or star party to go into what causes the different kind of spectrum features, but we could do that at some point. But what I wanted to really cover was just how we get the data tonight. I want you to see how at MSRO we actually get the raw data and then process it into a final image, which I think we'll have time on this Zoom session. This will be our last one tonight. I think we'll have time on this to show you the process by which I can stack those into an image, which will actually look a lot better. So any questions from anybody at this point? All right.
Not now.
I'm sorry, my volume must be low. Let me turn it up a little bit here. Okay, I think I'm good now. Okay, so if anybody has any questions, I think I can hear you now. Hayden, you wanna get online with this? No? You wanna say hi to everybody? No, you just want the dog. Okay. So let's see. So while we're waiting for the data to come in, I think I see a category here where I can show you some of our other spectrums that we've created. I believe this is an image. Yes. So when we get our spectrum, now this is not this supernova. This is Nova Cassiopeia, which we've been following since the spring of last year. But this is a good example of a spectra that shows those three different types of features. It shows the continuous, it shows the emission, and it shows the absorption. So this is what our spectrum will look like eventually when we prepare it for software analysis. Is we rotate it horizontally, we crop it so that we don't have the giant whole image to worry about. And we have to have the target star and the spectrum visible on the frame because the software that we use needs to know the spacing between the target star on the left and the spectrum on the right. That dispersion is very critical for calibrating our spectrum in terms of wavelength. And the program that we use is called RSpec for that. But let me show you this spectrum here. This is Nova Cas. I'm going to scale it a little bit differently so we can see some of those features I was telling you about here. Let me bring it down a little bit here. So notice there is a continuum, a smooth horizontal line in the background. That's the continuum. That's the continuous spectrum right there. But superimposed upon that, notice there's these little blips. They look like little dots. Those are emission features. Those are areas of the spectrum that are a lot brighter. And that's because they represent elements that are fluorescing in the atmosphere of that star. They're glowing. And the wavelength at which they're glowing at is an indication of the element that is producing those particular wavelengths, those spots. And as we analyze this Nova Cassiopeia, I can tell you that most of these little blips are due to hydrogen. They're the hydrogen Balmer series. This one over here on the right-hand side, that's hydrogen. That's the hydrogen alpha emission feature. This is the hydrogen beta emission feature here. This is hydrogen gamma right over here. There's other fainter ones that are in between. Those are actually helium emission lines. And there is even some fainter ones in here that when we plotted it, that showed other elements as well. So we were able to do that. So if you notice though, on the right-hand side, there's a dark line here, a dark gap. That's an absorption feature. That turned out to be not really inherent in the nova itself, but was caused by water vapor in our Earth's atmosphere. So that's an absorption line. That's an absorption feature that's created by water vapor. And you'll see that in some of our spectrums that are particularly when we're getting them when they're relatively low in the sky or when there's a lot of humidity. So you can actually get contaminations from the Earth's atmosphere in some of these spectrums that we get. So that's what this spectrum that we're getting tonight will eventually look like. Now, Nova Cassiopeia is a much brighter object than what we're imaging tonight. So even when we stack our images, it's not going to be as bright and clear as Nova Cassiopeia is. We just need a bigger telescope to do spectroscopy on faint objects. Unfortunately, we don't have a big telescope at this time right now. So we have to limit our spectroscopy to fairly bright stars, typically about 13th or 14th magnitude or brighter. Work pretty well. But once you get beyond about 14th magnitude, it gets really tough to get good data. Okay, so again, here's the galaxy NGC 4647, and here's the supernova, and here's M60. All right, and if we go up to the top of the frame, here's the spectrum for NGC 4647. It's gonna look like a featureless continuous spectrum because it's basically stars. Here's the spectrum of the supernova. And here's the spectrum of M60. If I go down in size, you'll see that if I go ahead and put it 50%, you can get a better idea of what the frame looks like here. So not a whole lot to really, you wouldn't be able to think you'd be able to tell a whole lot from this right now. But when we stack this, I do think it'll look a lot better. And we'll be able to get a usable spectrum out of it tonight. But that supernova is definitely fading. It's much fainter now than it was when we started watching it a month ago plus. It's definitely fading. And it's going to be soon, it'll be beyond our capability to do spectroscopy, probably within the next week or two. All right. So we have, looking at the camera control window, I'm going to move it so it'll highlight it for you. Camera control window tells us on the left hand, the middle box at the bottom, that we are on a image 11 of 30. So this data sequence is going to take 30 minutes to acquire. So you can see how you wouldn't think it would be a problem, but if somebody is using the telescope for spectroscopy or photometry, it can take a fair amount of time, of telescope time, to get the data that they need if they're looking at faint objects. And the good news is that at MSRO, we give them that time. We give our observers as much time as they need on the telescope. We don't charge anything for it. We hopefully will get funding at some point from a source that will allow us to continue to do this indefinitely. But right now we're doing okay with some generous donations of club members and MSRO commission members, and we've been able to keep up and running. So, and this is a resource that is available to members of the Rappahannock Astronomy Club. So if you're watching this video and you're thinking, geez, this looks kind of cool, I'd like to get into real science, but I'm not sure I know what to do. Don't worry. That's what we're here for. We're here to teach about doing real science with small telescopes. And we want to make these telescopes available to you as a member of the Rappahannock Astronomy Club, or as at large, when we get the donations coming in for the support that we need for this, to make these telescopes available to people, amateur astronomers, researchers from all walks of life all around the world. And maybe one of these days, we'll actually be able to get a bigger scope. What I'd really like to do is I'd like to have a 14 or 16 inch RC. And if we could get something like that, that would be the cat's meow, as they say. That would be really cool. But again, we'd need a bigger dome. We need a bigger structure than we have room for. I'd probably want it in a better location than where we're at right now. So it's probably better that we don't have a big scope like that right now. So we got 10 more minutes. That should be enough time to get a few more images. What I'll do is I'll cap this at maybe 15 images. And then we'll use the remainder of the time stacking. I'll show you how to stack the images. And then I can get the rest of the data afterwards. Hey, Bart. So my dogs heard Phoebe bark and they got all excited upstairs.
Somebody in a car.
So we have a new puppy now too. A little Pomeranian we drove to Ohio to get.
Huh?
So yeah, so she's fitting in very well. She's already the queen of the house, and even though she's just a tiny little 1.5 pound thing, she's got the mighty dog syndrome.
Yeah, mighty silly.
Yep. So her name is Zoe.
All right, so
I'm gonna get one more image here. We'll have 16 of them. Oh no, we'll have 15 of them, and then I'll show you how we can stack it. And that will eat up the rest of our time. Okay, I'm going to stop the data. So now what I'm going to do is we can close out that image, and we're going to stack those images. And Maximdale is a great program for doing that. And what you do basically is stacking basically is under the processing tab, and you go down to stack, and it's going to ask us what images that we want to stack. We have to add files. Now, one thing I didn't mention was that when we were bringing that data in, we were calibrating it. So those are calibrated frames. That's why I had to stick to 60 seconds. So we don't need to calibrate them in our stacking process. So let's go to the directory where our data is in, and it's going to be supernova 2020 HRS. Tonight's date 6:05, and here's where why we named the two different folders. What we did, we're going to do spectroscopy, and we're going to open up our 15 images. In the stacking. All right. I got to find the window. Here it is. It's this window right here. All right. And there's our files. They're all there. It looks good. We're going to line them by star matching. Even though it's spectroscopy, it'll actually look at the stars, and it's able to do that. Combine, we're going to do a median combine, and here we go. Now the image that's going to pop up on our screen should look a lot better than any of the raw images that we just looked at. There it is.
Yes.
Isn't that amazing how much better that looks now? Okay, so now we'll close that out. And what I'm going to do is I'm going to crop just the area around the, what I'm going to do first of all, let me rotate that. We got a little bit of a diagonal slant on there. So I'm going to rotate it just a little bit to the left, and that'll make the lines go up straight. That looks, I might want to rotate it just a little bit more. We'll go one more time, rotate again, maybe 2 degrees. Yeah, that's probably good enough right there. Okay, so now I'm going to save the image just so we've got it. Save, we're going to put it in the same category that we were in, group 1. I'm just going to call it spectra combined. So we know that's our, save it as a fits image. Okay, now I'm going to crop the image so that we just bring in the area around the supernova. It's going to save file space. It'll also make analyzing the software easier too when we import it in. Okay, now we're going to crop that. Okay, we're going to rotate it. Rotate right. All right, does that look familiar? That's kind of like that one that I showed you a little earlier. I know it looks a little noisier, but remember what I said. This is a much fainter object. Let's go to 100% here. Okay. So we have our target right there. There's the supernova. And we've got its spectrum right over here. It's very grainy, very noisy. This thing is getting faint. We're getting close to our limit, but that is a usable spectrum. We will be able to get data on that. Now, what I could do is I could process it a little bit to try to get some of that. Let's see here. Let's go smooth it out a little bit like that. No, that might be it. Okay, so as you can see, there's our spectrum. Definitely looks a lot clearer than what we were getting earlier. I would say this is probably about, the star is probably about 14th magnitude now. And that's about our limit here at MSRO for spectroscopy. So, because I can tell by looking at the spectra, we're getting pretty close. Now, again, this is only 15 exposures. If I was really doing this without being online like we are now, I'd get an hour's worth of data, and then we'd be fine. Okay, so we got a couple minutes left. I'm just going to go ahead and save the spectrum now. So I'm going to rename it because we've cropped it. It's going to be, I'm going to rename it the date tonight so that we know when the spectra was created. So it's going to be supernova 2022 HRS 2022-06-05, right? Because universal time, we're into the 5th now. And it'll be cropped and rotated. So we know that's the one that we're going to now, that we will import into our spectroscopy software. And I won't have time to show you how to do that tonight, but I'll send out the results so y'all can see the fruits of our labor of what we did tonight. Okay. Let's go ahead and I'm going to park the scope. Let's go ahead and look at our live webcam view here one more time. There she is. And we're going to go ahead and we'll park the telescope, put it away for the night here. So we go to our hand paddle and see where it says park scope there. We just click park scope. And if you look at the left-hand screen here, you should see the telescope. Barely you can see the telescope, but you should be able to see it's moving. It's going into its home parked position, which is pointing to the North Celestial Pole. Also looks like we've got some clouds out there too. I can see some clouds in the sky there in the north. We may have had interference from clouds tonight for all I know. Those spectras could have been compromised by substandard sky conditions. Okay, scope is parked. Notice the green dot here on the right, and tracking box is off on our hand paddle. So we're going to disconnect our scope, and it's now stored for the night. It's parked, and all I got to do now is push the turn off the software and push the structure, the cover back on it. Well, listen up, everybody. Thank you so much. I appreciate your time tonight. Is there any last minute